Am I audible?
Yes, sir.
Okay. Okay, then wait for a few minutes. If anybody join, then I will start. Okay, let me share my screen. Okay, is it visible?
Yes, sir.
Okay, mm, now is it visible that the notepad?
Yes, sir.
Oh, okay, okay. So let me start. Now I have to make the my own assignment, so that's why I prepare some questions to discuss this question. You have probably you have gone through that lecture, week one lecture. So based on that lectures, I prepared these assignments. Few questions I have prepared, and I will discuss this question. So let me start with very basic question first. You can also try uh, by your own, but I will also discuss elaborately. Okay. So we'll first I will write down the question, then we'll solve that. Okay. So let me write it in red. If there is any doubt, you can stop me and you can ask me question. Also, if you have any question regarding the lectures of week one lectures, then also you can ask me the questions. Okay. Verify whether dz equals to x plus dy plus y plus y into dx, sorry, is an exact differential or not. Okay. So this is the question. So first we have to understand what is the exact differential. Already the exact differential is discussed in class. Still, to solve this question, I'll discuss little bit the background of the exact differential. Then we'll solve this question. So we know that for the state function, basically like entropy, enthalpy, or internal energy, this kind of properties of any state is basically state function. So these functions are exact differential. What is the definition of exact differential? Let's say f is a function which is an exact differential, any f. So then if let's say f is function of x and y, if f is function of x and y, or for be consistent with the question, let we consider z. Z is a function of x and y. It can be any form of x and y, but it function of two variables x and y. Then we can write d2z del x del y equals to d2z del y del x. I will discuss what does it mean, but this is the condition to be an exact differential. If any variable not follow, obey this condition, then we can say that is exact differential. Okay, so z will be exact differential of x and y. Then it should follow this relation. So first we have to understand what does it mean. Okay, this is called this relation. It has a name, Euler's formula. I'm not writing, but I state it. So now let me derive this first. What, not derive, what does it mean? First, we have to understand that, then we'll discuss this problem. Okay. So now, as z is a function, so we can write function of x and y. We can write dz will be del z del x y dx plus del z del y x dy. Okay, this is trivial to understand. Means you can think like this: dz is change in z. Okay, so now z is a function of x and y. So how does z change? Z will change when x and y is changing, right? So when x and y will change, z will change. So we can think like that there are two contributions. If x is changing and y is changing, so we are thinking in that way. Let's say when x is changing, y is constant. That does mean that this part y is constant, x is changing, and when x is changing, then obviously z will change. That part is this. And other part, when x is constant and due to change in y, z will also change, and that is this part. And when you multiply with the dx and dy, then we will get the overall change. You can also understand it graphically, but it's trivial to understand from this equation, this form of equation as well. So now, if this is the case, then you can write it like m dx plus n dy, where m is del z del xy and n is obviously del z del yx. Okay, so now the exact differential z will be exact differential. The condition is stated like this: z will be an exact differential if, what is the condition? That, so we can write is z dz equals to m dx plus n dy. So condition is del m del y constant x equals to del n del x constant y. So this is the condition. Okay, so we can also write it. We have to just put m. So what is m? M is del z del x y, del z del x y x equals to, so this can also be written. So this is, in short, we write here are two derivatives, so that is del 2z and it is del y del x. This is equivalent to, okay, equals to del 2z del x del y. So this is the formula. So this is the definition to be an exact differential. So main definition is this, and this is just hand waving for to write down that long expression, but it means the same. So now we have to ask that this function dz equals to a, x dy plus y dx, this is an exact differential or not. Before that, uh, let me say why that state function is related to this exact differential. We have studied that if there is a state function, as I mentioned at the beginning also, that if there is a state function, let's say z is a state function, then z will be an exact differential. Why? Because state function means that, let's say z is a state function, it changes from a to b. So we can go, or for more pictorial way, we can understand like this. We have to go from here. This is a, and this is a, and let's say this is b. We have to go there. So we can go in this path. Also, we can go. Let me change the color. Also we can go through this path. Now, as it is a state function, and let's say in z, at z point, the z is the value of z is za, and at zb, at b it is zb. Okay, so it is converting to za to zb. So we can write dz is essentially be zb minus za, something like this. So what if it is state function, then this dz does not depend on the path. It can be through this path or this path, any path. It will be same. So it is the path independent factor. Okay, so we can think like that. Uh, so it does not matter, it will not matter whether we are changing first x or y. This equation means first we are changing x constant of y. After that we are changing with respect to y constant of x. And this means exactly opposite. First, it means that change of z with respect to y for constant of x, and then we are measuring the change of z with respect to x constant of y. So these changes, both changes should be the same if it is a state function. Okay, that's why state function should follow this equation, which is conditioned to be an exact function. Probably it is understandable. Details we can do the mathematics and all, but we are not getting into that. So now we have to check what we have asked to check, that z is given like x dy plus y dx. First, we have to see that this is a function of x and y. Z is a function of x and y. So we have to check z is exact differential or not. So that we have to check this relation. So first, we have to evaluate that left hand side. Left hand side is just this. Okay. So we have to evaluate this part. Okay. Sorry, this is right hand side, and it does not matter. You have to check both sides. So del z del y, from here we can easily find out what is del z del y. Del z del y constant of x is del y x dy plus y dx, and constant of y. So y for first term it's x, and for second term y is constant. So we can write it y del x del y. Okay, so we can write it. So here if we put, then del x will be, del z del y will be x plus y into dx dy when y is constant. So first term will give us 1, and second term, as y is constant, 1. So it will give us just 1. It will give us 1. Probably, okay, here x is constant, not y is constant. Okay, there is a mistake. X is constant here. Okay. So now if x is constant, so it will give us just x. And as y x is constant, so dx will be 0. For x is constant, this equation can be understood like that. Dx, if x constant, then obviously dx 0, so it will give us just x. Sorry for inconvenience. So this is x. So now it is 1. Okay. Now for the other part, we have to calculate del y del z del x. Okay, so here first we have to evaluate this part del z del x for constant of y. Again, we can understand if y is constant, so obviously dy is 0. So if dy is 0, it will be only y dx. So d dx of y dx. So it means just y. Okay, so if you put it here, then you will get just y, and it again gives the 1. So we can write what we can write. So directly we can write that. So d dy x, this is equals to, okay, so it means that z is a state function. Okay, so this is a state function, z is a state function, and also z is an exact differential. Probably it's clear. This is our first question. So let us move to the second question. Okay, first I write down the question, then check volume is an exact differential or not for ideal gas. Okay, the similar type of question, we have to check volume is an exact differential or not for ideal gas. Okay, so again, we know for any gas, let we are considering some gas. What is the properties of this gas? Not properties, what is the functions? Which functions defines a state of the gas? So we know from our HS class 2 level, we know that volume means V, pressure means P, and temperature. Correct. These three defines basically a state of a gas. And for ideal gas, there is the equation. We know that PV equals to nRT. This defines a ideal gas, an ideal gas. This is ideal gas equation. We know we are very much familiar with this equation where R is universal gas constant and N is number of moles. So what does it mean? It means that we are we are mentioning here there are three functions, right? V, P, and T. But there is a equation which relates three functions, P, V, and T. These are related to each other. It does mean that exactly two variables are needed to describe a state for an ideal gas, obviously, because this equation is valid for an ideal gas. Means that if you give me P and V, then obviously we can identify the P from this equation. For if we know the number of moles, that's in our hand. N we can fix, right? So we are not considering N right now. If you consider only P, V, and T, then that is related to this equation P equals to nRT. For 1 mole of gas, let's say N is not there. Okay. So PV equals to RT for 1 mole of gas. For 1 mole. Right? Now that means P, V, and T are related. That means if you give me P and V, we can evaluate P, and also if you give me VP, we can evaluate P. It means that there are essentially two variables, two independent variables. Okay, here I have written that there are three variables, but that three are not independent. They are related to one equation. So independent variable, only two independent variable. I think it's clear. It may be PT, it may be VT, it may be PV. That depends on us. So now, so we can write V is equal to RT by P, which means V is a function of pressure and temperature. R is constant, so V is obviously a function of pressure and temperature. Okay. Uh, so now, if this is the case, if V is function of pressure and temperature, 1 minute, probably my that screen is not visible. Here, probably I have to pin it. Uh, Sorry, hold on. Let me connect. Oh, it's okay. Okay, so V is equals to, yeah, V is function of P and T. So if this is the case, V is function of P and T, so we have to now check whether V is an exact differential or not for ideal gas. So if this is the case, then we can write. So similarly, we'll solve previous question. Del V del PT dP plus del V del TP dt. Okay, so this can be written. Now, if we have to check whether this is an exact differential or not. So our first, then we have to check this. This means that del del P del V del TP this. So first this part, what will be this? This is easy, I think. Del V del TP. What is del V del TP here? V is RT by P. So del P of RT by P for constant pressure process. So it's actually R by P. Now if you put it here, R by P, R by P, temperature, there is no temperature. So R is constant, it will be minus R by P square. Clear? Now for other side, it is del to be del P del T. So now it is del to be del T del P. Yes, so it's equivalent to del T of del V del PT P. Okay. So similarly, we have to solve, we have to evaluate this part del V del P P. So it is del P of what is V RT by T at constant temperature now. So it is minus RT by P square. This is easy. These derivatives are easier. So now it is del P of minus RT by P square. Now the P is constant, so it will be minus R by P square del P of P. So it is minus R by P square. So both are the same. R by minus, this is also minus R by P square. This is also minus R by P square. So we can write clear. So from here we can conclude that, what we can conclude that V is an exact differential. But this should be because V is a state function, and we already know that for any state function that will follow the Euler's relation, that means that will be a state function. That will be an exact differential. Okay. So now going to the third question. What is the third question? Let me write it. Reduce the form of the first law of thermodynamics for following process. Which are process? First, isothermal. Second is adiabatic, and third is isochoric. Okay. So what is the first law of thermodynamics? There are several expression for first law of thermodynamics because there are several our consideration we can say because there IPAC, the international convention is there, but in physics there are some different convention. We can understand what does it mean. So we'll consider our IPAC convention here, which says that the del U is basically Q plus W. Means del U is the change of internal energy, Q is the heat, and work W is the work done. But also it can be written as du is equal to d cross Q plus d cross W. Okay, these are the similar. Okay, why cross? Because these are not exact differential. This Q and W are not the exact differential. Okay, but U is a state function, so it's an exact differential. Okay. Now for IUPAC, we have to remind that if this is a system, if this is a system, if heat is going inside, if heat is going inside, then obviously Q will be positive because system is getting the heat. Okay. So then Q will be positive. Now if heat is going from the system, then Q will be negative. Similarly, if this work is done on the system, then the work it is positive because system is getting the work. But if system is doing the work, then it is a negative. So it's totally from system points of view. Okay, so in that way we can understand. So now this is d cross Q plus d cross W. So we can consider this form or this form, or we can also just I am saying that it is the form du plus d cross W. This form is used in physics. Okay, but here over everything is in terms of our surroundings. That's why there is the sign convention. Other is but the theory, the science, total science is the same for each and every equation, each and every form. But obviously, the sign convention is important. Otherwise, you will get the different equations, different numerical results. But we have to be consistent. That's why we are considering the IUPAC nomenclature, not nomenclature, IUPAC convention that I have mentioned here. So we'll follow this IUPAC convention. So that the sign is consistent. Okay, so now they have the question, it is asked to be to reduce the first law of thermodynamics for various processes. Okay. First, isothermal. Change the color. Isothermal means there is no temperature change. Isothermal, iso means constant, thermal means temperature here. So for isothermal processes, the dt is 0. Why I can write d? Because d is the state function. Okay, before that, this equation can be written as d cross Q minus PdV, because we know for mechanical work only that d cross W, the work done, is minus PdV. P is here actually P external, the external pressure. Why minus PdV? Because we are considering IPC nomenclature and we are seeing from the system perspective. So if system is doing work, then obviously that will be negative. Let's say if volume is expanding, we can think like that. Volume is expanding, then dV is positive. First layer, let's say this is V1, and if it is expanding to V2, okay, so that means that dV is greater than 0, volume is expanding. So if dV is greater than 0, if you put it here, then obviously d cross W will be negative. it means that system is doing the work. That's why it's negative. As I mentioned before, if system is getting the work, if you done a work on the system, then d cross w will be positive. So totally it's looking from system perspective. That's why it's considered as minus p external dv. So this is the form d cross q minus p dv. Now for isothermal process dt is 0. So what we can think like that? What does it mean? It means that if dt is 0, then there will be no change in internal energy, this U. Okay. Because internal energy, what does temperature means? We have to first understand. Temperature is actually average kinetic energy. We can think like that. Average kinetic energy of the gas molecules. In kinetic theory of gas, probably we have studied that average kinetic energy is related to the temperature. That is the true definition of temperature. So essentially, it's related to the internal energy. Okay, because we will see later for a question. We'll see how to calculate the internal energy, how we can calculate the internal energy. For obviously for ideal gas, we can calculate, because in ideal gas there is no uh, interaction between the molecules of the gas molecules. That's why we can easily calculate the internal energy for the ideal gases. But in general, for real gas also, we can calculate the internal energy properly, but it is trivial to understand that it's related to the kinetic energy, or not kinetic energy, total translational energy, vibrational energy, the definition of internal energy. This is including all kinds of vibrational, rotational, translational, all sorts of energy is called the sum of all sorts of energy is called the internal energy, and obviously that represents the temperature of that particular state. So that's why T essentially means is related to the internal energy. So that's why you can write here the temperature T is related to U, internal energy. But we don't know how it's related. For ideal gas, we can evaluate some form, but for general case, for real gas, we don't know. But we can say that it's related. Now, if dt is 0, essentially it means that for isothermal processes, du is 0. Clear? If du is 0, then the first law will be d cross q plus, sorry, not plus, minus p dv equals to 0. Means d cross q equals to pdv. Okay, so this is our reduced first law for the isothermal case. Let me go to the second one, adiabatic. Adiabatic means the system is isolated. That means system is not interacting with the surroundings through heat. It will not exchange heat with the surroundings. If that is the case, if heat is not exchanged with surroundings, then obviously d cross q is 0. It's trivial. So if d cross q is 0, then essentially we can write that du equals to minus pdv. So this is the first law, reduced first law for the for our adiabatic case. Okay. And for third one, what is this is isochoric. For isochoric means the p is constant. That means dp is 0. So it does not add anything, because essentially here p is we are considering the mechanical work, and mechanical work means the expansion or compression that obviously happens with respect to constant pressure. So it does not change our first law. It does not reduce our first law rather. But for isobaric, it should be the question should be isobaric. For isobaric means the volume. No. It Sorry. Pardon me. For isobaric means pressure is constant. Sorry, but for isochoric process, volume is constant. That means the dV is 0. So if dV is 0, then obviously du equals to, from here, you can write du is equal to just d cross q. This is our reduces first. Okay, but 1 minute. Why this is happening? This screen is too. It's okay, but this is not coming. Oh no, it's on. Okay, let me continue. That is okay. So this is the third question. Now for okay, now fourth question. This screen is visible, right? It's important. For adiabatic reversible process of an ideal gas, we have to prove three relations. First, PV to the power gamma minus 1 is constant. Second is PV to the power gamma is constant. And third one is T to the power gamma, e to the power 1 minus gamma is constant. So we have to prove three relations, right? So this is very, very important question because in class, obviously, that first lectures, uh, this was discussed, but probably due to some technical glitch, this part was not there basically. So this is important. So here, few things are very important, just like we have to consider for adiabatic process and the reversible process and for an ideal gas. Okay, so let me solve this question. First, we have to understand adiabatic process. As I discussed previously, that adiabatic process means adiabatic process implies that d cross q is 0. That means that is not interacting with the rest of the surroundings with respect to a heat. That is not exchanging any kind of heat with surroundings. So this is adiabatic process. And reversible process, we know that very small amount of change is going on there. So that's called a reversible process. And ideal gas, and it is ideal gas. So obviously it will follow the ideal gas equation, that is PV equals to nRT, or for 1 mole it's PV equals to RT. Okay, so now we have to prove it. Okay, so what will be our first law? Now first law will be, du equals to minus PdV, because obviously d cross q is 0, sorry, du, it is a d equals to minus PdV. Yes, I just, okay, du is equal to minus PdV. If it is, then we can write what is du. Now du, we can write it del u del vt dv plus del u del tv dt, because u is actually function of volume and temperature. So we can write it internal energy. Obviously that will be function of volume and temperature. It is u. We can write it. Now this is del u del tv. This is Cv. We know. Okay. Molar heat capacity at constant volume. This is Cv. So we can write it del u del Vt dV plus Cv dt. Importantly, this is ideal gas. And for ideal gas, what we have considered, what we know that for constant temperature, if temperature is constant, then internal energy will not change for ideal gas, as I discussed before. Probably I need to say that for ideal gas, obviously, here we have discussed for the ideal gas. For ideal gas, if temperature changes 0, then obviously du is 0. Now, so it is for ideal gas, we can rewrite this equation as dv equals to cv dt. This is very, very important lesson. Okay, this is general equation. Okay, means this is for ideal gas only. General equation, but for ideal gas. Now, if you plug that equation, what we will get that here, if you plug that equation, then we can get, so cv dt equals to minus pdv. Clear? So what now, if you integrate it from v1 to v2, then it will be v1 to t2. What is p? pv equals to nRT. If pv equals to nRT, then p equals to nRT by v. So it is nRT by v dv, v1 to v2. Okay. So, okay, before that, okay, we'll put integration later. Let me do it first like this. This is clear. Cv equals to pdv, just we have put p equals to minus nRT by v, nRT by v. So p should be going that way. So cv dt by t equals to minus nr, these are constant, dv by v. Now you can put the integration both sides. This is better to do, mathematically correct. So what we will get? This will be cv ln T2 by T1, and this is minus nr ln V2 by V1, considering Cv is independent of temperature. Then only we can bring out Cv from integration. So if this is the case, then what we can write, Cv ln T2 by T1 equals to, we know for ideal gas Cp minus Cv equals to nr. This proof has been done in class. Cv minus Cv equal to nr for ideal gas. So this can be written as clear. So ln T2 by T1 equals to Cp minus Cv divided by Cv ln V1 by V2. This minus sign is absorbed here. This was minus, so now it is V1 by V2. So ln T2 minus T1 equals to gamma minus 1, because gamma is defined as Cp by Cv into ln V1 by V2. Clear? So ln T2 by T1 equals to ln V1 by V2 to the power gamma minus 1. We can write it, because when we take log, then gamma minus 1 will be coming out in front of the ln V1 by V2. So now if you take anti-log, then what we can write, that T2 by T1 equals to V1 by V2 to the power gamma minus 1. So from here it can be written that V1 V1 to the power gamma minus 1 equals to T2 V2 to the power gamma minus 1. So in general we can write that EV to the power gamma minus 1 is constant. Then only we can write this. Okay. So this is the derivation, TV to the power gamma minus 1 is constant. Okay, this is the first relation. Now for second relation, if TV to the power gamma minus 1 is constant, okay, not from there, from here we can also write, now T1 V1 to the power gamma minus 1. This can be written as, we know that this is for ideal gas, PV equals to nRT. So we can write for state 1, P1 V1 equals to nRT1, number of mole is not changing. So now T1 should be, you can write T1 V1 by nR. So if you put it here, then we can write it T1 V1 by nR and V1 to the power gamma minus 1. So if you write it, then P1 V1 to the power gamma by nR. Similarly, P2 V2 to the power gamma minus 1 can be written as P2 V2 to the power gamma divided by nR. Now these are equal. Hence, P1 V1 to the power gamma by nR is equals to P2 V2 to the power gamma by nR, which essentially means that P1 V1 to the power gamma equals to P2 V2 to the power gamma. Hence, PV to the power gamma is constant. Okay, and the third one, this is also you can do in the same procedure. This is for T and P. Okay, so similarly here, if you do that, P1 V1 to the power gamma minus 1 equals to So here P1 V1 equal to N at T1. So similarly, we can write P1 V1 equals to N at T1. That means V1 is actually N at T1 by P1. So if you put it here, then you can write it P1 into N r P1 by P1 to the power gamma minus 1. That means N r to the power gamma minus 1, P1 to the power 1 minus gamma, and P1 to the power gamma. And similarly, you can write P gamma minus 1 equals to P2 into N r P2 divided by P2 gamma minus 1. So it is N r to the power gamma minus 1, P2 to the power 1 minus gamma, P2 to the power gamma. And again, these two are same. So you can equate these two. If you equate, then you can get Nr to the power gamma minus 1 equal into P1 to the power 1 minus gamma. P1 to the power gamma is essentially equals to Nr to the power gamma minus 1, P2 to the power 1 minus gamma, and T2 to the power gamma. So this will be cancelled out. So you can write P1 gamma, P1 to the power 1 minus gamma equals to T2 gamma into P2 to the power 1 minus gamma, which essentially signifies that P to the power gamma, P to the power 1 minus gamma is constant. So these three relations are now proved. Okay, so very important these three relations are. So we had to prove it. So now going to the next question. Question number 4. This is very not 4. This is question number 5. This is very important question. Prove the thermodynamic equation of state. What are the thermodynamic equation of state? First one is del u del Vt equals to E minus E into del P del T V minus P. This is first thermodynamics equation of state. And the second one is del H del Pt equals to minus T into del V del Pt plus V. So these are the thermodynamics equation of state, and we have to prove it. This is also very important. Okay. So, okay, and these thermodynamics equation of state are for any gas, not for ideal gas. For this is general equation. We can reduce for ideal gas. We can derive what the form of the ideal gas, but this is the general equation. Okay, this thermodynamics equation of states. Okay, so let me start. So for this is del u del v t. So we know first law. What is first law? That du equals to d cross q minus pdv. This is the first law. So if this is the first law, then we have to just uh, yes, del u del vt, if you put it, so from second law, what do we know? That d cross q equals to tds. Okay, S is entropy. This is discussed in the class, right? These are discussed in details. So I'm not going to discuss here, but S is entropy and D cross Q is the heat change is totally related to the temperature entropy change. So that's why we can write it. Okay. So now, if this is the case, then what will be the form? Then so we can write du equals to TdS minus PdV. Okay, this can be written probably there is no confusion. Du equal to TdS minus PdV. Uh, there there is some tricks. I will discuss that later. After this question, probably it is needed to discuss. From that tricks, we can derive easily this kind of relationships. But we will go into that. Before that, we have to solve it. Derive this question. Now del u del vt. So from here, del u del vt. So t is constant, so it will be del s del vt minus p. We can write it. Okay. So what is del s del vt? Okay, no, here we have to discuss that. So here I have to introduce, not introduce, I will discuss the thermodynamic square. Okay, there is a concept. This is kind of tricks, thermodynamic square. This is a trick to calculate these differentials. This is like this. Okay, this is called the thermodynamic square. From here, we can easily derive the relations, but it can be derived by using our first law, yeah, using our basic knowledge or basic equation, we can derive, but that is too elaborate to derive. But easily we can derive from the square. We have to derive this del s del vt, right? So del s, I'm discussing the tricks here, del s del vt. So just we have to identify this del s del vt means s vt. We have to read like this s vt. So s vt, s vt, like this. So we can like write like this s to v then t. Okay, now that will be equals to, just we have to you have to draw in this way. Let me draw. It may be confusing first time to listen, but it's easy to understand. This edge should be shared. The last edge should be shared. Here is VT, right? So is this VT edge should be shared. So it PTV. So PTV. And this arrow is considering both the edges, this right angle and this right angle, both are consisting this arrow, these sides of arrow. So if these sides of arrow is consisting, then we have to put a minus sign for both cases. So we can write it this. If you put it here, if you put it here, del s del vt equals to del p del t v. So it can be written as, essentially this is the first equation. So from here also we can also derive some other equation that is important to derive. That's why I have drawn it carefully. So this edge, there are essentially four edges, right? This edge give this equation. Now going into other edges. Let's say this edge. what does it give? So there are first these, which means del S, del P, T. This should be related to this. The A should be shared. So this should be equals to del V, del T, P. Just look it again. We have to consider here SPT, SPT, del S, del PT. We have to read like this, del S, del PT, according to this age. Now, from this age, the last age should be shared. So del V, del T, P. Now, if you look at this is consisting this arrow, so there will be minus sign, but this right angle does not consist. So this is the relation. Okay, this is done. Now the next stage, probably let me choose other color. What does this edge gives? First one is this and another one is this. So we can write it just like this. First will be del V, from starting here V, SP del V del SP. It should be equals to, from here, TPS del T del PS. Now both are not consisting arrow, so there will be no minus sign. This is another relation, and there are only one edge, this edge. So similarly, here will be two right angle, this one and this one. So first one is going like this and second one is going like this. So again we can write the first one del P del S. Probably now it's clear how it can be written, and both are, one of is consisting, this is consisting this arrow, so there will be a minus sign. So there are four equations. These are called Maxwell relations. Okay, so these relations are called Maxwell relations. These Maxwell relations, these Maxwell relations can be easily remembered or easily can be derived using this Maxwell square or the thermodynamic square. This is important. Okay, so now we have derived this, the first thermodynamics equation of state. This is, now we have to derive the second one. So clearly it is related to, second one is related to H. So we have to write the H first. What is the DH? What is H? H is enthalpy defined like U plus PV. Clear? U plus PV. Okay, one more thing. This is called the internal pressure. This is called pi T. This is pi. U by V is called pi, the internal pressure. Now H equals to U plus PV. So now what we can write from here, it's very important. DH is equal to du plus PdV plus VdP. We can write it. Now we know what is du. Du is TdS minus PdV. Just we have discussed du is equal to TdS minus PdV. If you put it here, then you can write it TdS plus VdP. If dH is that, then from here what we have to derive? Del H del PT. So del H del P E. It will be essentially T is here, del S del P E plus V. Again del S del PT. Del S del PT, where is del S del PT? This is del S del PT equals to minus del V del TP. Just we have to put it, then we can write minus del V del TP plus V. So this is the second thermodynamics equation of state. Okay, this is important. These two thermodynamics equation of states are important. So now we have to go our next question, the sixth question. Okay, so that Cp minus Cv equals to P into del P del T V into del V del T P. Again, this is an important question. This kind of question can be formulated considering various equation we have to derive. So now again we have to derive this equation. Okay, let me start. This can be done easily, but okay, let me solve elaborately. What we know that from first law of thermodynamics, du is d cross q minus pdv. This is known from first law of thermodynamics, and from second law of thermodynamics, it's known that d cross q is actually equals to tds. Clear? If it is the case, then okay, in that way we can derive, but that will be more longer. Don't need. It's not needed. Just we have to. What is Cp minus Cv? This was discussed in uh, class, right? There is a relation between Cp minus Cv. We have to use that relation, and uh,
R.
yes, yes. Is there any question?
Cp minus Cv is equal to R.
Yes, this
Is equal
was
to R.
equals to R, but this is for ideal gas, right? Cv minus Cv equals to R or NR. This is for ideal gas. In general, there was a relation, right? That was derived in class. If you we can derive it here again. What is the Cp minus Cv? This Cp minus Cv relation is very important. Do you remember that, or should I derive?
You can go with the derivation. I can,
Okay,
let's see it.
okay, okay. Let me derive it. Then we need that equation I have written, right? U equals to d cross q minus pdv. This is our first law, and d cross q equals to tds. This is our second law. These relations are needed to derive that equation. So now, what is Cv and what is Cp? Cv is actually the molar heat capacity at constant volume. So this is actually d cross q divided by uh, dt at constant volume. Because definition of heat capacity is the amount of heat needed to increase the temperature by 1 degree. Uh, so that's why it is d cross q by del T at constant volume. This is Cv, and for Cp it is d cross q by dt at constant T. These are the definition of heat capacity Cv and Cp. Now, if you look at for constant volume processes, d cross q, if you put the for constant volume, it's easy to understand. To constant volume, dv is 0. So if dv is 0, then first law of thermodynamics will be reduced to du equals to d cross q, because dv is 0, so this term will be 0. So essentially, it implies that Cv should be equals to du dt v. Okay, because just I have put that d cross q equals to du, then it will be du dt v. But for constant pressure process, dp is 0. There is no pressure change as such. So if dp is 0, then here I have written, right? Yes, this form, dh is equal to tds plus vdp. So for constant pressure process, we know that dH equals to, uh, let me write it again, H equals to U plus PV. If it is U plus PV, then dH is equal to du plus PdV plus VdP. Now for constant pressure process, this term will be 0. So it's only du plus PdV. So du plus PdV. Now we have to put the first law of thermodynamics. This is actually d cross q. Just look at it here. From here, you can write it that first law of thermodynamics says du equals to d cross q minus PdV. Hence, d cross q equals to du plus PdV. So if you put it, then easily we can write du plus PdV equals to d cross q. That means for constant pressure process, dH and d cross q are the same. This means that for constant pressure process, Cp should be equals to dH by dt. This was the definition. Just I put d cross q equal to dH. So we can write, two things. Cv equals to du dtv and Cp equals to dH dtp. These things we can write. Okay. Now just we have to derive it easily. What we have to do now, we can write it. What is H? H is U plus PV. H is U plus PV. So if you put it, then okay, U plus PV. Sorry. So it is del U del TP plus P into del V del TP. So the first part del U del TP, this is actually equals to CV, and this is P into del U del. Okay. So now, so what we can write, Cp minus Cv. Okay, no, 1 minute. Sorry. I think there is a problem. Yes. Okay, this is del U del T P. Okay. Sorry, but in CV it is del U del T V. There is a difference. So now we have to replace it. For ideal gas, it's easy. For ideal gas, del U del VT is 0. So easily we can do that. But here, this is not for ideal gas. This is for general. So for general cases, we have to follow strictly. We can't input any restriction, any kind of any condition of ideal gases. We have to keep in mind that always that this is not ideal gas. Okay, so now we have to write it. So del U del TP. What is del U del TP? Del U del TP, we have to first understand, evaluate, not understand. This is it. So now du can be written as del u del tp dt plus del u del pt, I think, to cvd. Okay, no, I have written it here. Previously I have written. We have to just rewrite that. 1 minute. Yes, this equation. This is the du, right? Du equals to del u del vt dv plus cv dt. This is we have to. So cv dt plus del u del v t dv. If it is, again we can check what was, this is u and this is v. Let me check again if it is correct or not. Yes, cv dt and del v del u del vt. So it is cv dt del u del vt. Correct. Now it's right. So del u del, what we have to evaluate, del u del tp This is so del u del T equals to, this will be Cv. Just you have to divide it by T. Then it is del u del Vt, and this is del V del Tp. Just I have divided with del T. Now, if you put this in this equation, then what will be Cp? Then obviously, so Cp will be Cv plus del u del Vt into del V del Tp. This part I have put plus P into del V del Tp. Okay. So Cp minus Cv equals to, if you common it, del V del Tp will be common. Then it is del u del Vt plus P. So this is the main relation. Now, if you put for ideal gas, that is the special case. We can also derive that. Change me the color. For ideal gas, before that, just this equation is very important. You have to keep in mind that always. This equation, thermodynamic equation of states, this equation always we have to remember. Otherwise, that, because to derive this equation, you can see, I remember this equation, but to derive this equation, I have to do lots of work. So this is not trivial, always trivial to derive. This will cost some amount of time. So that's why, to reduce that effort, we should remember this equation. We can derive it, but that is not needed. If we remember that, then it's easy. Okay, for ideal gas, P equal to nRT. So if it is P equal to nRT, then del u del V del Tp, this term, del V del Tp, this term will be del T of V, means nRT by P. So nRT by P means nR by P. And for ideal gas, we already discussed, for ideal gas, del, this is 0, because for constant temperature, this is constant temperature, internal energy change is 0 for ideal gas. So this part will be 0. So obviously Cp minus Cv will be nR by P into 0 plus P. That means nR. These lessons we remember very well, but this is for ideal gas. This is not general. This equation is general equation, valid for any gases. But what was our question? Our question was, yes, this, we have to prove this one. Now it's easy to prove. We know this equation. Now we have to just put the thermodynamics equation of state. What was the thermodynamics equation of state? Thermodynamics equation of state 1. Two thermodynamics equations of state was there. We have to use the first one. What was the first thermodynamics equation of state? Just we have derived in last question. This is del u del Vt equals to this one. Just we have to put it. Del u del V T equals to T into del P del T V minus P. This is the thermodynamics equation of state. First thermodynamic equation of state. Now we have to just put it. Del u del Vt. This is also del u del Vt. Now put it. Or we can, let me do one. So you can write it. This is this part. So this part is equals to this. So Cp minus Cv will be Cp minus Cv del V del Tp. This is del V del Tp. And this is equals to P into del P del Tp. Or we can write. So this was asked to prove. So this is also very important question, because this kind of question usually asked to derive various kind of relation. So we have to derive that kind of relation using our known formulas. Okay. So now the question number 7. Okay. Okay, this question is very important also. Calculate adiabatic index of methane gas at high temperature and very low temperature. Okay, this question will require very different kinds of knowledge. Okay, but this is very important question because this will address how to calculate the CP and CV. We are discussing CP and CV various different way, but we don't know how to calculate it. For ideal gas, we can calculate, and we'll do it here. For ideal gas, how we can calculate CP and CV, and this is important. Here, though it is mentioned as methane gas, but we will consider that methane gas will behave ideally. Otherwise, we can't calculate. Okay, so let me go through it. First, what is the adiabatic index? This is actually gamma. Gamma is called adiabatic index, means CP by CV. We have to calculate the gamma for methane gas. Then high temperature, low temperature, we'll look it further. But first, we have to calculate CP by CV. What is CP and what is CV? So, what is definition of CV? Just we have derived del U del T V. This is CP, and for CP, it is del U, not del U, del H del T P. This is methane gas, but we will consider methane gas as ideal gas. Okay, means for ideal gas, Cp minus Cv is Nr. Okay, so first we have to calculate the Cv. If you calculate the Cv easily, you can calculate the Cp just using this relation. So what is to calculate Cv? To calculate Cv, what we need to calculate the U. If you calculate U, then by differentiating with temperature at constant volume, you can evaluate the Cv. So our intention is to calculate the internal energy. Energy of an ideal gas. How you can calculate? The internal energy is written as U or E. Here we will use the E to be consistent. So E will be for gas molecule, let's say there are various gas molecule. So in gas molecule, which kind of energies are available? If you ask, then it should be translational energy, rotational energy, and vibrational energy. Means that gas molecule will translate each other, that is the kinetic energy. Rotation, gas molecules rotate, so that is rotational energy, and also the molecules are vibrating. For if it is monoatomic gas, let's say helium gas, that means one atom is identical to one molecule, helium gas. So there is no vibrational energy. Vibrational energy will be there for more than one atoms are included in molecule. Then there will be vibration between molecule, then EV will be there. But this is for methane gas. Methane gas, so there will be non-zero EV. We have to consider that. But how we will calculate ET, ER, EV? These things we have to calculate. For that, we have to calculate, very importantly, number of modes. Just we have to calculate number of modes, and we have to multiply number of modes with half kT or half kBT, where kb is the Boltzmann constant, T is the temperature, then we can get the energy. Okay, so this is we have to calculate. So how we'll calculate number of modes? First, for this is very important. We have to understand it. For a molecule, rather a gas molecule having n number of atoms, will have total 3n number of modes. So total 3n number of modes will be there, because we know that there are 3 degrees of freedom for each molecule. Let's say there is a molecule, so there will be 3 degrees of freedom, x, y, z. If there is n number of atoms, n number of atoms, then there will be 3n number of modes. Degree of freedom will be 3n. Now for translational. For translational, number of modes will be 3, because a molecule can go in x direction, y direction, z direction. Here we are discussing with a methane molecule. How does it look? This is a methane molecule. This methane molecule can go in x direction, in y direction, or z direction. Is there any option? No, there is not any option. So number of modes will be 3 for any molecule. It can consist 1,000 number of atoms, but totally number of modes for translational energy will be 3. Clear? For rotation, okay. If it is linear molecule, then number of modes will be 2. Or if it is non-linear molecule, then number of modes will be 3 for rotation. Okay, it can be understand like it can be understand. Let's say this is a linear molecule. So how it can rotate? This can rotate in that direction. One option. Okay, or it can rotate in this way. There are two possibilities. It difficult to visualize, but if you think, uh, let's say a pen, that pen you can rotate only in two ways, because if it is a linear molecule, its rotation is on around its own axis. That is not uh, a rotation. Let's say, let me try to explain. X, Y, Z. So it can rotate. It, just understand around this axis. This rotation is not allowed here. It's allowed, but it's not a rotation actually. It's not changing its position. So that's why this is not considered. That's the reason this is 2. But for non-linear, there will be 3 degrees of freedom, 3 number of modes. Yes.
For, for monoatomic gas.
For monoatomic gas, also there will be. Okay, no, for monoatomic gas, you can think like this. For monoatomic gas, number of molecules is, number of atoms is n. N is 1. Okay, for monoatomic gas, n is 1.
Yes.
If n is 1, then total number of modes will be 3.
3.
And 3 will be coming from translational.
Yes.
There is no rotational, because to have rotation we must need at least 2 atoms. Otherwise, there will be no rotation, there will be no vibration, there will be only
Okay.
translation,
Okay.
right? Now for vibration, for linear, what will be number of modes? This is difficult to calculate, so that's why we'll use that trick. The total number of modes should be 3n. So it should be 3n minus 5, because translational has 3, it has 2, so total rotation plus transition has 5, and total should be 3n, so vibrational should have 3n minus 5. And for non-linear, number of modes equals to 3n minus 6. 3, 3. So total 6 are included in translational rotation. So vibration will get 3n minus 6. So E will be, first ET will be 3 into half kBT using this formula, number of modes into half kBT. Number of modes is 3 and each mode will have energy of half kBT, so it will be 3 by 2 kBT. E rotation, that will depends. If it is linear molecule, then it will be 2 into half kBT. So essentially it will be kBT. But for non-linear, okay, before that, for linear molecule, V will be 3n minus 5 into half kBT. No, here is a difference. It is not half kBT. Okay. For vibrational case, we have to multiply it with kBT because actually for translation, for rotation, each mode consists half kBT of amount of energy. But for vibration, actually there are two types of vibrations are there. Okay, I'm not getting to that details, but there are two types of vibration. That's why each mode will consist kBT amount of energy, not half kBT. So this formula is not wrong. This formula is correct, but for vibration, there are two types of vibration basically. That's why two will be multiplied. So which gives us kBT. Oh, okay. So that's why we have to multiply it kBT. So it is 3n minus 5 kBT. Now for non-linear case, rotation should be 3 into half kBT, which essentially gives 3 by 2 kBT. And similarly, EV will give us 3n minus 6 into kBT, not half kBT. It will be n minus 6. Okay, kBT. So now this is ready. Now we have to just calculate for methane gas. For methane gas. This is methane gas. CH4. So N is number of atom is 5. So total number of modes should be 15. Cn should be 15. Now we have to calculate Et first. Et should be 3 into half kBT. There will be no change. This is 3 by 2 kBT for any gases. Now E rotation. It is a non-linear molecule. So for non-linear molecule, it should be also 3 into half kBT. It is also 3 by 2 kBT. Now EV, as it is non-linear, it should be 3n minus 6 kBT as I discussed. So it is 9 kBT. So total energy E will be Et plus Er plus EV. So it is 3 by 2 kBT plus 3 by 2 kBT plus 9 kBT. So it is 12 kBT. If I'm not wrong, it is 12 kBT. Yes. Okay. So this is E. So CV is actually del U, del T, V, and D. E and E U is same. Just these are two different notation. So you can write it du de dt v. So this is actually 12 kb. Okay, but there is a thing. Okay, this energy. Okay, 1 minute. Right, these energies are for only one atom, not atom. Sorry, one molecule. This is for one molecule. This is on one molecule. Okay, but we have to consider the uh, CV. CV is what is CV? This is molar heat capacity. Means we have to consider Na number of molecules. We can think like that. E is actually equals to Na into U. Like sorry, this one. U internal energy is actually equals to Na into E. E is energy of one molecule and U is energy of one mole of molecules. So we have to multiply it with Na. Then it is actually 12 hours. Probably it's clear. We have calculated the internal energy. This internal energy E, this is for only one molecule. But we have to consider for one mole of gas because CV is molar heat capacity. CB, these are. So that's why we have to multiply it with the number of molecules, that is Na. So CV is 12 bar. So if CV is 12 bar, then what will be CP? CP will be CP minus CV is R or NR. We are considering one mole, so it's actually 1 R. N equals to 1. We are considering one mole, that's why we have multiplied with Na. These are 1 mole. So Cp will be Cv plus R. So that should be 13 R. If that is the case, so gamma is Cp by Cv. So 13 R by 12 R. So it's actually 13 by 12. So 13 by 12 ratio, we have to just find it. This is obviously greater than 1, we can say, but we have to find out the ratio. Let me calculate 13 by 1.08 something. So it's actually 1.08. But this calculation, what I have done here, this total calculation is actually for our high temperature. If you look at the question, where is the question? Yes, high temperature. Okay, at high temperature, as I mentioned, this is KBT. This is KBT. This total discussion, I discussed here. Total calculation is for high temperature, not room temperature. High temperature means it's maybe around 600 Kelvin or more than that. This is for high temperature. If it is low temperature, very low temperature, if it is very low temperature, everything will be same. What will be just changed? This contribution will be changed. This contribution of vibrational energy, this EV will be changed. So for low temperature, EV is number of modes, which is En minus 5 for linear molecule, and for non-linear molecule, EV is 3n minus 6. This is correct. But this contribution for high temperature is KB, P, but low temperature is 0. There is no contribution, so it is 0. This is for low temperature. So now you can calculate. So for low temperature, total E will be just ET plus EV, ER. So ET plus ER, what was ET and what was ER? 3 by 2 kBT, 3 by 2 kBT. So it is actually 3 kBT. So CV will be del U del T V. So it is Na del E del T V. So Na into 3 kb. So it is actually just 3 R. Okay, this is for low temperature. So Cp will be Cv plus R. So just 4 R. So gamma will be Cp by Cv. This is 4 by 3. Okay, from here we can calculate. 4 by 3 means it is 1.33. This is for low temperature. So one thing we have to remember, the contribution of Everything is same. If you change the temperature, contribution uh, in vibrational modes, that will be changed. Then EV is, this is correct, number of modes, but this contribution, this will be changed. Okay, just let me write. For high temperature, this will be kBT, correct? For room temperature, this will be 0.2 kBT. For low temperature, this is 0 kBT. Just we have to remind that. Otherwise, there is no option. We have to remind. So in this way, we can calculate the gamma. Gamma is that adiabatic index, as I mentioned. Okay. So now, what is the question number? It was 7. Next question, question number 8. Derive the Kirchhoff's equation. This is very important question again. Kirchhoff equation we have to derive. In class, Kirchhoff equations were used, but this was not derived. But this is very important relation. That's why I want to derive it here. First Kirchhoff equation is del ut equals to del u0, or we can write del u2 equals to del u1 plus u1 to t2 del cv dt. This is the first equation, and this is the second equation. Or you can write it like this. The same thing. These two are the Kirchhoff equation. This equation we have to derive again here. Okay. So here it's trivial to understand why U is related to CV and why del H enthalpy is related to CP, because as far we know that the CV is related to internal energy, and the pressure, CP is always related to our enthalpy change. Okay, so let me derive this. Okay, what is U? For the first question, du is actually CVDT. We know, for ideal gas. In previous question, we have discussed this. U is actually CVDT. Basically, CV is del U del T V. From here also you can write. But this is for ideal gas, because the total expression is this. But for ideal gas, this part is 0. That's why we can write it like this. Du equals to CVDT. So if du is equal to CVDT, then we have to consider del U2 and okay, now we have to integrate it. So let's say temperature is changing from T1 to T2, then we have to integrate it. So it will change U1 to U2. So we can write it del U equals to U1 to T2 CV dt. This is the case. Now for other cases, here there are two processes are involved. This question is very tricky. This Kirchhoff equation, let me go it elaborately. Okay. It seems very trivial, but there are two processes are involved basically. That's why this Kirchhoff equation is difficult to understand, but let me clear it. Let us consider first We have to think physically. A system. Let's say this is a system. This system, this is state 1. State 1, this is changing to state 2. How it's changing, we don't know, but this is changing. State 1 to state 2, it's changing. Here, for first case, the internal energy is Ui or U1. Here it is U2. Enthalpy is H1. Enthalpy is H2. Correct? So, if it is, then for this change is occurring. So now we can write what is del U. Internal energy change is U2 minus U1. U2 minus U1. You can write it. If it is, now this del U for these changes, del U and del H, if you change now the temperature, if temperature is, let's a total process is undergoing at a constant temperature, T, constant temperature. That means at constant temperature, you are changing state 1 to state 2. That's why internal energy change to U1 to U2 and enthalpy is changed to H1 to H2. Let's say you change this process first at T1 temperature. Clear? First you change it at T1 temperature, then there is a delta U. You measure the internal energy change, del U and del H, enthalpy change. That is H2 minus H1. This total process, correct? Again, you perform the same uh, total process. You perform the total process, changing the temperature at T2. Instead of T1, you change the temperature to T2. Clear? Then also you will get another du, another delta U. Get it? So then we have to just consider. Let me draw clearly so that it can be understandable. This is the rough drawing. So now let me draw it properly. Let's say this is our first state. This is state 1. State 1. State 1. We are changing to state 2. Clear? At T1. Constant temperature we are changing. Constant temperature we are changing. Okay? And also this is a constant volume process. Constant temperature and constant volume V. Correct? If this is the case, here the internal energy is U1, internal energy is U2. Okay? Now, you are again changing. This is again U1, U2, and this is the third state. Here the internal energy is U3. But for this change, volume is V, constant volume V, but constant temperature T2. Means you are starting with a state having the internal energy U1, this is state 1. You are changing this state to U2, state 2 having internal energy U2 at constant temperature T1 and constant volume V1. V is fixed. For each cases, this is the V. But when you change this constant volume process, state 1 to state 3, then this is the at constant temperature. If you change that constant temperature T1 to T2, then obviously the state will be changed because the internal energy is function of temperature. Okay, I think this is the overall picture. This is the overall picture. Whether is it visible or not? Yes, it's visible. So now you can write what you can write. Now let me zoom it again. First, del U at T1. What is del U at T1? U2 minus U1. Clear? And del U T2, this is U3 minus U1. Correct? You can write it. So, what we can write? In general, we can write that. So, del U is actually function of temperature. If you change the temperature, the del U is changing. Here del U is U2 minus U1, here U3 minus U1. So del U is function of temperature. So del U can be differentiable with respect to temperature. This is important. And overall process is going on at constant volume. So you can write it at constant volume. So this is the case. We have to measure this. We have to measure this. That means change of internal energy with respect to temperature. If you change that constant temperature for this constant volume process, then what will be the change in del U that we have to measure. Okay, so now it's easy. This physical picture is important. So you can write it del T of in general UF minus UI initial to final. Okay, so if it is, then you can write it del UF del T at V del UI del T at V. So this is CV, but for F, and this is CV for I. Means when let's consider this change. For this change, there is a CV. What is CV? CV is del U del T V. This is the constant volume process. So del U del T. This is yes.
Excuse me.
Huh.
In the during the process, we are considering constant temperature and constant volume. If
Yes.
volume and temperature is constant, the there should not be any sense of internal energy.
Uh, if no. Internal energy will change because you look at. Okay, let me discuss this first.
In
Yes, you
what
are.
way the internal, because
Wait.
there is no work,
Uh,
no
no.
input of
Mm,
I think there is no input of heat also.
oh, yes. 1 minute. Yes, it's a good question. Let me think whether is changing. Hmm. Yes, you're correct. You are correct. No. There is something problematic. No, I think there is problem in this physical picture. Mathematically, it's correct. You can do it here for mathematically, but for physically, yes. When the temperature is constant, V is constant, internal energy change should be zero. Yes. Okay.
Internal energy
Okay.
may have some other contribution also. Some other
No, we
contribution
are
internal
considering
energy
the
may come.
volume is fixed, right? So if volume is fixed, then obviously PDV is zero. If you look at the first law, then du is equal to d cross q minus pdv. Obviously, this is zero. This is also zero.
This is
Then
isothermal process. So
isothermal process, obviously. So essentially, d cross q is TdS. So it's pdv. Okay. This part is zero, correct? But no, TdS is there, right? So du will not equals to zero. Well, again, you can ask the question. If it is constant volume, let me clear. If it is constant volume, then obviously there is no
and
work
then,
done.
but again at the same time it is at constant temperature also.
Yes, constant temperature, but that does not mean that you are thinking of ideal gas.
Yes,
For
yes.
a- for ideal gas, it is zero because as I
Okay,
mentioned, for ideal gas, U is only function of temperature. If dT is zero, then obviously du is zero for ideal gas.
okay.
So this is
Yes,
not ideal gas. You can check with the first law. This is the first law, right? D cross Q minus PDV.
yes,
So what is D cross Q?
yes.
This is TdS, right? TdS minus PDV.
Yes.
So dV is zero, so it is TdS. So in entropy change may be there, right? At constant
And
temperature, du is TdS. Okay, so
okay,
this is not for
thank you.
ideal gas. I was also confused by, but the
Okay, sir.
question is good question. This is for not ideal gas, obviously. Ideal gas, there will be exactly na, for ideal gas, Cv is always constant. So if you do it, it will be Cv F equals to Cvi. So obviously this is
Yes,
zero.
sir.
Ah, but this is not for ideal gas. This
Yes.
is in general derivation. So now it's clear,
Okay.
right? So it can be written as del Cv. Okay. So del U del T V is actually del Cv. So you can write del Cv dt. Now just you have to take the integration u1 to t2. This will be del u1 to del u2. So del u2 minus del u1 equals to del Cv dt. This integration you can't open because this del Cv is function of temperature. This is not independent of temperature. So this should be inside the integration. So this is our Kirchhoff equation. Similarly, if you do for our enthalpy case, what will be the change? That will we have to consider the constant pressure process. Volume will not be fixed here. This is 1. It's changing to 2. Here the pressure is same, so volume should not be the same. So this is H1, this is H2, and same following the same argument. This is state 3, this is H3. So you can also think like that dH, what is dH? dH is equal to du plus pdv plus vdp. So du is actually d cross q minus pdv vdp. So this will cancel out, but it is constant pressure process, so this will be also 0. So again it is d cross q. So it's not TdS. So it is actually not non-zero. So for here also the same question can be arise, but this is non-zero again. So now similarly we can write that del H is again a function of del H again function of here temperature. The same procedure as we followed here, function of temperature. So what will be del T at constant pressure? So we can write it del HF del TP minus del H I del TP. So it is obviously CPF minus CPI. So it is del CP. Hence, what we can write? Del of delta H equals to del Cp dt. Just you take the integration u1 to t2, it will be del h1 to del h2. So you can write it del h2 minus del h1 is del C. So this is the second Kirchhoff equation. So there are two Kirchhoff equations basically. So just I have to mark it. This is second and this is the first one. Okay, these equations are used for various numerical problems, but these are the derivation of two Kirchhoff equation. So we have discussed all the question as I think, yes, right questions. So now for today, one question I leave for thinking. You can think the why the gamma is always 1. This we know. Okay, just let me just say it. Why gamma is always 1. That means why Cp is always greater than Cv. You can think why Cp is always greater than Cv. This is for you for thinking. And another one is what is the significance of entropy? This I will discuss next day for the first question. What is the significance of entropy? What does it mean? What does it guide? Why the entropy is needed? These things is very important. for describe a state of a particular system, entropy is very important, plays a very important role that we'll discuss in next day. But this question, this is easy. Why Cp is greater than Cv? You can't prove it. You can prove it considering ideal gas, but I'm not saying to that. But theoretically, you can argue that Cp should be always greater than Cv. You can think like otherwise I will discuss in next class. But this is very important, significance of entropy. This first I'll start next class discussing this significance of entropy. Then we'll go through the other problems. Okay, and also probably the 2nd February is a deadline for submitting the first assignment. Uh, and my next class will be after that submission date. So I'll discuss some question from that assignment also, the difficult questions. And I'll also add questions from my side, and I will discuss some 8 to 10 question in next class also, starting with the description of entropy. What is the importance of entropy, significance of entropy. So in this class, let me stop here. If there is any question, you can ask me.
Okay, thank you, sir. Thank you very much.
Okay, so let me stop here. I'll stop sharing. Then you can leave. So now you can leave and I can disconnect it.